Welcome to part 1 of our 6-part series on the Z-transform. Before we can dive into the mathematical mechanics of what the Z-transform does, we first need to understand the environment it lives in, the world of discrete time signals. When you speak it into your smartphone, your voice travels as a smooth, continuous sound wave. However, computers cannot store infinite data. Instead, they slice that smooth wave into a finite list of exact numbers. Imagine tracing a continuous sine wave. If we only measure its height at specific, evenly spaced moments in time, we create what is known as a discrete signal. We write this discrete sequence as x of m. Let us define this mathematically. A continuous signal, x of t, is sampled every capital T seconds. The resulting sequence becomes x of n, where n is simply an integer index that counts our individual samples. At its core, x of m is just a simple array of numbers. For example, at indices m equals 0, 1, 2, and 3, our discrete signal might hold the exact values 1, 2, 0, and -1. Because these signals are essentially just arrays of numbers, they are perfect for digital processing. We can easily slide a mathematical window over these discrete samples to compute moving averages, filter out noise, or detect patterns. But there is a catch. If our sampling process is too slow, we will completely miss the true shape of the original wave-in effect known as aliasing. We must always sample fast enough to capture the real details. Two fundamental discrete signals will appear constantly in this course. The first is the unit impulse, a single isolated spike at m equals 0. The second is the unit step, which turns on at 0 and stays at 1 forever. In the continuous time domain, engineers rely on the Laplace transform to analyze complex systems. But as we transition into this digital, discrete time world, the Laplace transform is replaced by its powerful counterpart, the Z-transform. To recap, discrete signals are nothing more than sequences of numbers tracked by an integer index n. In the next video, we will finally introduce the exact mathematical definition of the Z-transform.